This is an extra credit project that was turned in, and I'm going to turn the screen on here. I don't know if you know Victoria Hayes. She's really has a talent for making things look good, building things, designing things. When we had our homeroom competition, she helped design the door project and all that. And so she she was looking for something for extra credit on this last chapter. And again, she'll say she didn't do quite as well as she wanted to. That's why, it's not like, hey, I think I'll just sit around and build one of these models, So she did have a reason for it, two reasons. Said, I'd like to get some extra credit points. She did. So I didn't tell her how to build it, but she had to go and get the materials. And I don't know can you see it? It's on the screen yet?
Yeah.
And so she drew the sodium chloride as ions. She had to decide, what color to paint them. She's going to paint them. And then she made her water. There you go. Got some water molecules up here. She showed the slight positive, slight negative, the polar molecules there. So I thought that was a pretty well done. Can everybody see it? And she has a little diagram there. So I like that. Okay. Okay, so here's what we're going to do. This is where you want to, this is, like I said, the last chapter we're going to do. So I'd like you to get kind of get down into the business a little bit. This chapter is different. So we really won't mention the mole at all. Moles won't be at all in this mention. This is a whole new ball game, this last chapter. And it's called Modern Atomic Theory. We already talked about that a little bit. Even though it said modern, most of this was developed in the early 1900s, early 20th century, early 1900s. And people like Einstein and Heisenberg and Schrodinger. Anyway, you'll hear some of these names and you'll find out what they did. So we're not here to study the physics as much. We have a little bit of physics in this chapter, but we're not here to study like the deep physics of it. So if you ever took a higher level physics class, you might study that. Okay, so you'll hear me use this term here, the quantum mechanics model of the atom. And that's what they call the modern atomic theory. And it has actually answered a lot of questions that we had. A lot of the applications you guys have, like your cell phone, that kind of thing, have to do with the quantum mechanics model. So the first thing I'm going to show you is, here's a picture on this page here. And you say, I see a neon light. Now, I will eventually tell you why is there a neon light in this chapter. And we're going to talk about that. I'll actually set up a little demonstration for you, and I'll actually show you a neon light, and I'll put some electricity through the neon, and you'll see how it glows, and we'll talk about what that means when it glows like that. The other thing I mentioned is there are really kind of like 6 ideas in this chapter. One of them is the nature of light. Do you know what light is? 2, what happens when electrons or when where they're supposed to be in the ground state, or what happens when they get excited. We'll talk about that. I would make a list. And I'm going to make a list right here in my book. As we get to a scientist, I'll go ahead and try to add a new scientist to my list right here about what each scientist did to help understand the modern idea of an atom. And this is a thing called electron configuration. I remember that word scared me the first time I heard it, but look at my tables. My tables in this room have a configuration that's different than the tables next door. So what do you think configuration means? My tables are configured different than the tables next door. What do you think that word means? What is it?
Order.
The order or arrangement, right? The arrangement. So when I talk about electron configuration, we'll look on the periodic table, and every one of these elements have their electrons in a slightly different configuration. It's just a little bit different than the one before it. And that's the pattern. That's what I want to spend more of my time on the pattern that you see in electron configuration that they discovered. And the last one, you put these together. When you look at the periodic table, can you link these 3 things together? And can you tell me what the trends are? Like, do you know that if I go from lithium, or hydrogen, lithium, sodium, potassium, rubidium, cesium, if I go down, it's called a group or a family. If I go down a group, what happens to the size of the atom? You might want to take a guess on that? If I showed you, if I went down group number 1, if I went down group number 8, what would happen to the size of the atom? I haven't taught it to you yet. Do you have an idea, a guess? How about a guess? John, you got a guess? What do you think would happen? Think the atoms would get bigger, smaller, or bigger than smaller?
Probably
So, well, I don't know. I never thought about that.
probably bigger.
Okay, and I think like you might be right. Like
Might get light bigger, but it talks about to be light smaller.
I think they probably. I'll tell you, they do get bigger as you go down.
I knew it.
But what's interesting is when you go across a period, that's like going from number 3, 4, 5, 6, 7. If I go across a period left to right, the atoms actually get smaller. So it's kind of interesting, and we'll talk about that. That's one of the last things we talk about in this chapter. So I want you to open up your minds a little bit. When you're starting a new concept, you can't rely on what you've been doing the last 3 chapters. You can't rely on that. We've got to start all over in a way. All right, we're talking about this guy named Rutherford. Rutherford was around 1900, experiment was about 1911, I think it was, something like that. And so what he did is, we did this in the first semester. And do you remember Rutherford's contribution to this? He had this thing called the gold foil experiment, where he had this radioactive material that would shoot out little bullets you couldn't see, and the bullets were little positive particles. And when it hit a screen, it would make the screen scintillate. It would make it glow like little sparks, okay? Like little glowing, I should say, like a little twinkle. And then he put it was a thin piece of gold, but it was a solid piece of gold. And he put it right in front of that beam of radioactive material, radiation. And you would have thought that it would have blocked most of the scintillations over here. But it was almost just as bright as it was as if he didn't have the gold there. But then he also saw something else. He saw some scintillations going this way and over there, and even some back here. And he said, I don't know how to explain that. And the only way he could explain it was, he said, the atom must be mostly emptiness. It must be a lot of nothingness, because most of the little bullets went straight through the atoms. But every once in a while, one of my bullets would be deflected. Well, I know my bullets are positively charged, so there must be something that's really small in there that has a positive charge. And that was the first time any scientist thought that the atom had a nucleus. Now, even in elementary school, they probably teach the nucleus, don't they? So nobody knew that before. They thought the electrons and protons were all just mixed up like a plum pudding, right? And so anyway, that whole idea was Rutherford's idea that it had a nucleus. And the nucleus had a positive charge, and it was very dense. Like 99.99% of the mass of the atom was in the nucleus. That means a whole lot of the nucleus weighs almost nothing and takes up most of the space, but there's a lot of empty space, isn't there? Well, then we get into this right here. We talked about waves, and I said I'd get this out, and I'll go ahead and get one of these out. So I'll make some waves today. Okay. So one thing they like to tell you that you need to study waves before you can do this chapter. Okay. But what's interesting is this wave and waves of the ocean and sound waves, the ones that are hitting your ear right now, those are all what we call mechanical waves. That means the energy travels through a particle to another particle and to another particle like that. And so if somebody, you want to help me, Davis? Davis, can you help me here? Okay, you're going to take the end there, and we're going to put it on the roller. Right, keep on going. Go back. Go way back. Go way back. Keep going. Keep going. All right, here you go. Now lay it down.
So long, dude.
This is not the kind of slink you buy at Toys R Us, no. All right, take a look. What I have is a bunch of particles, and what I'm going to do is set up a wave. So you're going to hold yours still. Okay, ready? And here's one kind of wave. Now, if I do that steadily, can you see a wave length? Look at the top of one wave and the top of another wave. The crest of one wave, the crest of another, or the trough to the trough. That's called a wavelength. Now, what I'm going to do, that was a fairly long wavelength. Let me see if I can get a short wavelength. Okay, watch now. You see how that was a shorter wavelength? Here's a long wavelength. right, here's a short wave thing. Okay, ever see that? All right. That just so happens, like I said, I'm not your geology teacher, but when earthquakes can happen, there are two kinds of waves occur. One of them is like this, and goes like that, and that shakes buildings up. And another one is like this. I'm going to pull some of these back and let go of it. Now watch. I'll do it again. All right. I'm getting a little tricks in here, a lot of tricks. You see it go down there? Okay, now I have a little piece of paper taped there because I want to show you that it looks like part of the slinky is going from my hand all the way to Davis's hand, right? It looks like it's going his hand. But if you look at that piece of paper, what does the particle do? It actually just goes back and forth, doesn't it? So what's traveling through the wave? The wave is not the particles traveling, it's actually the energy traveling through the particles, isn't it? Okay, all right, let go, and go ahead, ready, go. One. Ooh. Okay, again, a little bit bigger slinky then.
Where do you get one?
Yeah, where can I, like, do they have these on, like, maybe Amazon?
Oh,
Yeah, you could buy anything. You can buy Amazon, on Amazon, but it could be an extra long slinky. This is kind of like a physics teacher would have.
But like science
Let me show you. Let me show you another wave. This one. Let me get the book out of the way for a minute. I'm going to put a little dish here. Can you see a dish on the camera? Yes. All right, these. You ever seen these? Okay, I'm going to do another wave, and this one's a little bit different wave. It's going to be a sound wave, and what you do is you don't really want to hit these on a hard surface. So I'm going to go like this. Now you say, that's not doing anything. Yeah, because you look at your eyes and say, well, it looks a little blurry, but no, I don't. That's not doing anything, isn't it? Watch out. That thing's really vibrating, and when I set it in contact here, it starts vibrating the table. And then the table starts vibrating the air, and the air sends out sound waves, and you can hear it. Now, see if you can watch this. This would be very dangerous and don't ever do this, please. Don't ever go like that and like put it next to your tooth. I know you're thinking, it's not going to do anything. It'll actually chip your tooth. All right, here we go. Watch the water. Did you see that or not?
Yeah.
Watch again.
Can you do one more time, please?
I don't have slow motion, so I hurt.
You on my phone if you want to
Ooh. Okay.
want to record it.
Yeah. All right. Get your camera like right there. Ooh, this will be good. Okay, so I'm gonna lay it right there. So you focus right down there, okay? You tell me when you're ready. And
Yeah.
Ready? Ooh. Okay. So back it up. Let me use your camera on the camera here. Go ahead. You set it up. All right. Push.
It's fine. It's just like slow.
Okay.
It's about it.
Back off a little bit. So the thing's it's really vibrating a lot. And I'm really not a music. I like music. I love music. I never played an instrument except for drums. And this thing is vibrating at 320 vibrations per second, which is unbelievable. Anyway, this is a tuning fork, and they have different kind of things. It used to be, now they have electronic. I think some of your phones probably have apps, don't they? Any of you play guitar? Doesn't your phone have an app that you can, thanks. Does somebody have a phone app where you tune your guitar? So they actually have a thing that you're supposed to play a certain chord, and you put your phone out there, it hears it and it says, oh, it's off a little bit. Nobody plays guitar in here?
Yeah, I'm not a big guitar
Oh.
guy.
Here, point to the guitar person.
Andrew Gabriel plays guitar.
Okay.
So you might want to ask him about
Nobody in here.
it. And Kyle. Kyle Sampson.
You look like you play guitar.
Yeah, Kyle's a big guitar producer.
Kyle and Andrew both play.
Okay. All right, so here we go. So let me go ahead and let's go to the next page. And what I want you to know on this page, and I've written a lot of things on here, but try to get the idea of what this is. The good news about studying the waves, like the Slinky wave or the other kind of wave, you can actually point to it. I can point to it. There's a wave, there's a crest, and there's a trough, and there's a wavelength. I can do that. And but the kind of wave that light travels in is it's an electromagnetic wave, and it doesn't have to travel through anything. It can travel through nothing. So the light from the sun, it goes all the way through the vacuum of space, and it goes all the way through. It doesn't have to go through anything. So it is a little bit different kind of energy, but it does travel in waves. They believe it did. And I told you about this controversy that's been going on for 300 years. What is light? There are experiments showing that light must be little BBs of particles. But there are other experiments that says, no, particles wouldn't do this. Particles don't bend around a pole, but waves do. And so, which is it? Is light a wave, or is it a particle? Well, the modern theory says that it's both. It's called the dual nature of light. It's a particle and it's a wave. And nobody likes to hear that, but we're going to talk about that. This right here is what they call the EM spectrum, the whole electromagnetic spectrum. So anytime you read a book or a question on a test, and it says, looking at the electromagnetic spectrum, if you don't like saying that or your brain doesn't like it, just replace it with the word light. The electromagnetic energy is light. You get it? So the electromagnetic spectrum is light. Everything on here is light. Gamma rays are light, X-rays, microwaves, infrared, ultraviolet, radio waves. Those are all forms of light. They all travel at the speed of light, which is an unbelievably big number, like 186,000 miles per second, or 300,000 kilometers per second. That's huge. Now, one thing I want you to know about this is that of all the different forms of light, the really, really small wavelengths are here. And that's like, it says 10 to the minus 12th. That's a trillionth of a meter. That's a tiny, tiny wavelength. That wavelength is so small that if I had two atoms here, the wavelength could go in between the atoms. Gamma rays can go right through your body. X-rays can go right through your body. You get that? You know why it's harmful, though? As it goes through your body, it also encounters chemicals and things in your cells, and it actually destroys a lot of chemicals. And if you're exposed for just a little bit of time, you probably won't notice it. The longer you're exposed to gamma rays or X-rays, more and more cells will die. And when enough cells die, then you die. If you have too many cells of your liver die, you'll eventually start getting sick and you'll die. Or too many cells of your brain. So anyway, what we find out is that these are all forms of light, but your eyes can only pick up a really narrow band, this really narrow band of light here, and this is called the visible spectrum, and you call it a rainbow. So the rainbow is like the visible spectrum to you. And here's Roy G. Biv backwards, R-O-Y. No, see, you guys learned Roy G. Biv in middle school, yes? Red, orange, yellow, green, blue, and I don't know what indigo. Yeah, I do. Indigo and then violet. Violet's actually very dark, but this blue here is like indigo. So anyway, and some teachers don't even want to show you indigo. So they'll say Roy G. Biv. They'll go BV instead of BIV. Have you ever had a teacher do that? Just leave out indigo? I don't want to explain what indigo is to them. Okay. So what we found out, and this is something that's not in the book, and I want you to draw it in there. Every year I've asked people to put this in the book, just in case, and it should have been in here, this little equation here. If all these forms of light travel at the speed of light, the speed of any wave is equal to the wavelength times the frequency. Everybody got that? Wavelength times frequency. Now, I don't know how much math you know, but I'm going to show you something that's not, it's mathematical, but it's not, you might not hear it in math class. Okay, here we go. I'm going to set up an equation just like that. Ready? 10 equals 5 times 2. 10 equals 5 times 2. Why are you doing that, Mr. Feeney? But I'm going to play around with this equation. Watch what happens. If this is a constant, then I'm going to leave it as 10. But I'm going to make the wavelength get twice as big, 2 times bigger. Now, if that has to stay at 10, and I made this get 2 times bigger, what does happen to the frequency in order for this to be true? One more time. 5 is the wavelength, 2 is the frequency. If I made the wavelength longer, if you have a longer frequency, if that gets bigger, what happens to this number? What happened to it? It got smaller, didn't it? As a matter of fact, this got 2 times bigger, this got 2 times smaller. And that's a fancy word. It's called inversely proportional. Wavelength and frequency are inversely proportional. What does that mean to you? If the wavelength gets bigger and bigger and bigger, wavelength, what happens to the frequency, how often that wave occurs? If the wavelength gets bigger, what happens to frequency? Everybody. It gets smaller. So, look right here. If I had a really, really big wavelength, like radio waves, 10,000 meters long, man, that's a huge wave, isn't it? It would have a certain amount of frequency, okay. But what if I made the wavelength smaller and smaller and smaller and smaller? What would happen to the frequency? You know, Daniel, you know. Bigger and bigger, wouldn't it? The frequency here would be huge, huge. And it just so happens that frequency and energy are what they call directly proportional, meaning if you get bigger, I get bigger. So here's something you have to know about this chapter. You have to know this about light. As the wavelength of light gets smaller, the frequency gets bigger. If the frequency gets bigger, the energy gets bigger. So which one of these types of light would actually have more energy in them? 5 seconds of radio waves hitting you, 5 seconds of visible light, or 5 seconds of gamma rays? Which one would actually deliver more energy to your body? The wavelength gets smaller and smaller and smaller. The frequency gets higher and higher and higher, and the energy gets higher and higher and higher, right? So which ones would hurt you more? A 5 second blast of radio waves, visible light, or gamma rays? Okay, part of this chapter is knowing that. If you can remember that, you're going to be okay. All right, and I'll say it more than once. So they eventually figured out that light seems to have a dual nature. And so they had a name. They had a name for this little particle, this little bundle of energy. They show that light travels in little bundles of energies, and those are called photons. Have you had that before? Okay. I was at the airport the other day, and the security stopped this photon. And he said, hey, where are you going? He said, no, you don't have any luggage. He says, I'm traveling light. But anyway, so photons are particles, little bundles of energy that travel at the speed of light. And what I want you to know is that if this is the wavelength for red light, and this is the wavelength for blue light, which of these photons would have more energy in them? Which photon delivers more energy? A red photon or a blue photon? Blue, okay? Because look at Roy G. Biv. See this? This is a high wavelength. Sorry, this is the 700 nanometers. I write that on there. This is about 700 nanometers, and this is 400 nanometers. And so anyway, into here, between 400 and 700 nanometers is, God said, that's the only kind of light I'm going to let your brain understand. They have evidence, though. They have evidence that other animals can pick up wavelengths that you can't. I can't believe it, but they actually hooked up a camera to like a bumblebee eye and able to see what they see. And so bumblebees can actually see ultraviolet. I can't see ultraviolet, but they can. And so when they started looking at a field of flowers with a special camera called an ultraviolet detector, they said, wow, that flower looked kind of dull to me. But when I looked at the flower under the camera, it's like the flower went like this. Hey, it was like an arrow. Hey, come this way. You want some nectar? Okay. And actually, the flower looked different under ultraviolet. They think other animals might be able to see infrared. Infrared. Now, we're smart enough. God gave us a brain. We can actually make a camera that picks up infrared. You get that? And it changes the infrared into a color I can see. And so we can actually, quote, see infrared with a special camera, or ultraviolet. So anyway, so this blue light would have more energy per photon than red light. Okay. Now, you okay on this so far? All right, so I'm going to get ready to turn the page here. This is where we get into the main idea of the chapter, okay? So here we go. I did something like this on a demonstration where if you take certain chemicals, do you remember like lithium? I had some lithium chloride. It was in a solution. The chlorine ions didn't do anything when I excited them. I couldn't tell that. But the lithium ions actually gave off a red flame, didn't they? Yes, no? Do you remember that or not? And those are called flame tests. Now, why are you doing that? Why are you giving off colors? Now, when I set up my demonstration for tomorrow, I'm going to show you something like this. And yet, I know you don't believe me yet. That's okay. Even though I might see red light with my eyes, let's get back to a little physics here. We call this white light, okay? This is called white light. Newton, long time ago, Isaac Newton, he actually got more famous studying lenses, mirrors, and prisms. It's called optics. He got famous studying that first before he did his laws of motion and gravitation, that kind of thing there. Newton is a real famous painting. Here's Newton in a room, and he's got the curtains drawn. There's a little chunk of curtain cut out. And so a single beam of bright sunlight's coming into the room. And here's Isaac Newton holding a triangular piece of glass. You know what that's called? What's that triangular piece of glass called? A prism, isn't it? It's a prism. And if you hold it just right, the light, that little beam of light will hit the prism and it'll bend. Now, the bending of light is called refracting. Not reflecting, but refracting. If you bend it enough, then the individual colors, and nobody knew this before Newton, so the individual colors of white light will be separated. And for example, the violet has small wavelengths. When you put it through a prism, it goes, Weir! It likes to bend a lot. And red kind of goes, oh, okay, I'll bend a little bit. And so if you let it go through a prism, it will not only bend the light, it will separate the light into the Roy G. Biv. And so here's this famous painting of Newton, a light coming through a little piece of curtain, hole in the curtain, hitting the prism and shining a rainbow onto the wall. And that was really famous. He said, light is really made of many colors. But when they hit our eye at the same time, it looks like white light. And then some people said, come on, I know what you're doing. That glass has something in it that's coloring the light. You're coloring the light. The light's not made of all those colors. I would know, wouldn't I? And so what he did, he got another prism, turned it upside down. And ready? Rainbow. And then he hit the next prism, and they all went back into white light. See, if the glass was coloring it wouldn't go back to white light. So there's some really neat experiments that were done in physics that helped eventually these people here. Okay, so here we go. This is the hardest part of the chapter in a way. We have electrons. We have electrons in an atom, and we'll talk about where they are. But let's pretend that just let's say it's a single hydrogen atom, and he only has one electron. If he's sitting around like in this room right now, there's only a certain amount of energy in that atom. Okay, now, what would happen if I were to excite that electron? You say, well, how do you do that? How do you excite an electron? Well, you can use microwaves. I could use a Bunsen burner. I could use a flame. I could use electricity. There are different ways to excite an electron. Okay, so look up here. Everybody here? All right, now, let's say this electron, this is called energy, okay? how much energy does that electron have? Let's say it has this normal amount of energy. It's in its ground state. Okay, got that? All right. How is hamburger analogous to an electron that's not excited? How is hamburger analogous to an electron that's not excited? Nobody? Anybody? They're both in their ground state. You know what ground beef is? Well, anyway, here's an electron that's not excited, and so it's in its what they call ground state. And so now, here's what's interesting. We're going to hear about some scientists that did some experiments, and Einstein was one of them. And they found out that if you try to give this electron some energy, it might ignore it. Hey, I'll give you a little energy if you'll jump up to here. And it goes, no, not jumping. Nope. All right, I'll give you this much energy if you'll jump. We get that? They found out that you cannot get an electron to be excited a little bit, and a little bit, and a little bit more. You can't do that. It doesn't do it. But if you gave them this much, energy, it will jump to another level. And that's called a quantum of energy. It'll make a quantum leap. So watch here. Electrons, here I am, normal electron, my ground state, give me some energy. No. You give me a quantum energy, whoa! Then I'll jump up to here. I'll absorb that energy, and I'll jump up to an excited state. Now this is crucial for the chapter. I want to make sure I don't lose you on this page, okay? Nothing happens. When this thing jumps to the next level, it absorbs energy, and you won't see any difference. But then the electron is going to jump back down to its ground state. Now this is what's interesting. When the electron jumps back down to ground state, instead of absorbing energy, what does it do? It releases energy. And sometimes the energy it releases, I can see it with my eyes. So some elements, when you excite them a certain way, I'll see you giving off energy. Your excited electrons. Now, what happens then is the electron would go back to ground state, and if the energy is still there, it would go absorb again and go boom, and go boom, 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 boom. See that? And guess what? It would continually give off a certain color light, wouldn't it? Now, I need you to know that because there's a fancy word they use in this chapter. It's called, they said, energy is quantized. Energy is quantized. And what they mean is this. Electrons will not jump a little bit. If you give them this much energy, they'll jump. Electrons don't do this. You can't take an electron and say, get a little more excited, a little bit more, a little bit more. It's like a ramp. No, it's not like a ramp. It's like a staircase. You give me this much energy, I'll jump. How about a little more? No. How about another quantum? Yes. Yes. And so it's quantized. The electrons can only be here, or here, or here, but not halfway. Now, you might think that's nothing. That doesn't mean anything to me. So let me show you this next page. All right, here we go. This is my demonstration tomorrow. So if you understand how this works before tomorrow, then when I do the experiment, you'll say, I understand that now. Here we go. Here's an electron down here in its ground state. Okay, and here's one quantum. Here's a quantum of energy. If it jumps up here, what else can it do? It can absorb energy here, but what else can that electron do? It can jump back down to its ground state. Now, look how much energy that is. All right, now watch it again. Watch again. Let's go over here. Here's an electron, and it can jump to here, and you don't see any color, but then it might jump back down. It might jump all the way to here, and it might jump all the way down. It could jump all the way down. So what if it jumps all the way down here? What if it jumps from here to here? What if it jumps from here to here? Okay, now here's what I want you to see. Tomorrow, you're going to see a light. It's going to look like a neon light. But I have this special pair of, it's kind of like Now, it's called a diffraction grating, but to you it looks like a peephole thing. And so what's going to happen is you can look at neon light and it looks orange. And you look at this and it spreads the orange out and you'll say, hey, there's more than orange there. You'll see this thing like that. Look at that right there. You'll see that light and that light. What? I didn't see that. It looked orange to me. It all hit your eye at the same time. But if you separate that light, you can see, and these are called emission spectrum or a bright line spectrum. And give me about 1 more minute, okay? I want you to tell me which one of these jumps down, which one of these down jumps are associated with which color, even though they're marked. Okay. Which one of these jumps down represent the highest amount of energy? 1, 2, 3, or 4? Which one represents the highest amount of energy that's going to be released? Can everybody see it or not? If you don't, raise your finger. How many fingers? Is it 1, 2, 3, or 4? 3. Okay, now, go up here. Tell me which one of those beams of light, which one of those light emission spectrums, which one has the most energy? And I told you had to remember that. Which one? This has the biggest wavelength, smallest energy. This has the smallest wavelength. So if you said number 3 was purple light, this would tend to give off purple light. What's the smallest amount of energy? 1, 2, 3, or 4? 2. So which one is that? That's this guy, isn't it? Now, that whole thing, when you see this tomorrow, you'll say, that's what that means? All right, well, thank you very much. Thank you. And, hey, I would go ahead. Listen, I would start the odd problems. I would start the odd questions. It will take you, you don't want to wait till the last minute on these.